adversarial noise, okay? So you are given images and then labels, right? And this is your discriminator. Okay? What does discriminator do? And let's say it has weights W. So it minimizes over W some loss which is of the discriminator. Let's say these images are X comma Y. Right? Xi's and Yi's, let's say n images. So, and I can represent it in matrix form. Right? And the loss could be your cross entropy loss or whatever it is, right? So this is what your discriminator is trying to do. And it is able to do it really well, which means your loss is going to 0, right? That was another exam question, right? If it's perfect discriminator, the loss is very close to 0. Okay, fine. Now what you want to do is an image xi, you want to add a noise, let's say eta I, let's say epsilon times eta I, okay? Such that the discriminator can no longer get the right predictions. So this I can I can say I want to get noise, let's say the images are normalized in some way, right? So such that you want to get eta ij, such that eta ij is, so your new image xi hat, I can write it as, instead of this I can write it as this times eta I, such that eta ij is less than epsilon for all I comma j. Right? So for all pixels my noise must be small, and I want to add this noise. Okay. Now what is your loss of discriminator? So loss of discriminator is summation over I xi once your model has been trained, right? And let's say W star are the optimal weights, right? Optimal weights of the discriminator. So I am summing over all the images. This is my loss of the discriminator. Now what I want to do is, instead of xi I want to give it xi plus eta I. Now I want this image to be misclassified. So how do I choose eta I such that the image has a maximum chance of being misclassified? I have to have first constraint, which is this one, that the noise cannot be too much, right? You can add anyway, you can add a lot of noise and make it, go bad. So this is one constraint. What's the other thing you can do? What if you wanted to to misclassify? What would you do? What's the most obvious thing you would want to do? Maximize the loss. So you are going to do a gradient ascent on LD xi yi, keeping the weights fixed. See, when you are doing gradient descent, when back propagation, you are looking at the output of every layer and finding its derivative with respect to the input of the every layer. Right? What is the notation we use? Zi, right? Zi del Zi by del Zi minus 1. That's what we compute. So you go all the way to the input. So you can find the derivative of the loss with respect to the input xi. Now I am changing the input now. I am not changing the weights. So I choose the input so that my loss is increased. So I do a gradient ascent on the input, but my constraint is I cannot make my eta I too large. So I'll cap my gradients with respect to input to epsilon. Right? And I do one iteration of gradient ascent on first image. I cap my gradients to the input, to the epsilon, and now I have a new input, so I'll have a new gradient. So again I can do gradient descent on this new input, and I can keep doing that until I can no longer increase or change my input image. Some of the gradients with respect to the ith component of the input, the signs may flip. So you increase, let's say, 1 pixel, later it turns out that you're decreasing 1 pixel. Then that's a good situation, because earlier you increase the loss, and by decreasing also you increase the loss. But once it gets saturated, once it hits epsilon, and then the gradient sign is in the same direction as epsilon, then you cannot add that anymore. So you keep finding the gradient for the pixels in the image where this noise is still less than epsilon. And once it reaches the epsilon for most of the pixels, that's your adversarial noise. That is one of the methods of doing it. Right? There are other methods also. See, we can be inspired by the gradient method that we did, right? So what does rprop do? We are saying when you backpropagate all the way to the first layer, the gradient becomes too small and it's not really relevant. So instead of looking at the gradient, you look at the sign of the gradient. So you can just look at the sign of the gradient and update data I as just epsilon times the sign of the gradient. That's another strategy. So like that you can come up with multiple strategies. So as long as you update eta I such that eta I times the sign of the times the gradient is a positive number, then you are good. Then you are actually adding adversarial noise. Okay? No? Not clear? Huh? Yes, no? Yes. You are not getting. You have an issue. Okay. So let me do just very quickly. So del LD, let's say xi, yi, w star with respect to del xij. This is what you find. And you say eta I is min of this comma epsilon if del LD by del xij is greater than 0, and this is max minus epsilon if del LD by del xij is less than 0. Right? If my gradient with respect to input pixel is positive, then I update eta I as just the gradient, some step size, right? Some step size. How do you represent step size? What's the notation you use? Huh? Eta. Okay, so that's taken here. I can use some other. Let's say, I'll just use step size into that. Step size into. Okay, and here also step size into. Okay. So you can say eta I is equal to min of eta ij plus step size into this gradient, and here it is max of eta ij plus this if the gradient is negative. Right? So you don't want to get it less than minus epsilon, you don't want it to go more than plus epsilon, and then you keep repeating this step. So this you will put in a loop for all j, and then you put a root. Another loop you put it in, and you keep doing this update. Okay? I'll share some references that actually talk about adversarial noise.
This is the training algorithm.
This is the algorithm to generate adversarial noise. Right, but in the second step you are going to generate adversarial noise directly with using xi, using the image, using the input image. So you are going to again, use this loss to train your generator. Right, and the discriminator is going to be using the same loss as before. Okay, fine. So today we are going to quickly cover recommendation engines. I'm not going to go into much more detail. I'm just going to give you a very high level overview because there's a lot of things to cover. We cannot go in details of this, but this will enable you to do your assignment, right? You can look into the references and go through those things. I'll just cover main issues, and later if time permits, maybe I'll cover a little bit on some of the approaches, but yeah, we'll start with this. So, there are different types of recommendation system. What's a recommendation system? We'll start with that and then talk about different types of ratings that you have. Very important concept in recommendation is how do you get the feedback from the users. And they are implicit or explicit, we can talk about it. And then the content-based and collaborative filtering. These are two main classes of recommendation systems. And we'll talk about that. And then there are these matrix and tensor factorization approaches. And then nowadays there are very advanced techniques that are also coming based on deep learning. And then we talk about evaluations and challenges, okay? So, this you all know, recommendation systems are very kind of ubiquitous. When you go to like Amazon, you buy a product, it shows you other products like that, that's a recommendation. You go to a movie site, it recommends you movies. You go to Google, the search that comes, the pages that come, you can think of it as a recommendation system. The ads that they are shown, you can think of it as a recommendation system. You go to a Facebook page, you see these ads. You can think of those ads as recommendation systems. You go to YouTube and you watch a movie or you watch a clip, you watch a video, and then it shows more videos. That's a recommendation system. You go to TikTok or whatever. Is it not banned? Is it banned? Huh? Insta and TikTok, right? So you watch something there, reel or whatever, and then you swap, the next reel that comes is a recommendation system. Right? So they are kind of ubiquitous. They try to help the businesses to increase their diversity of products sold, if they want to, that is. So what can you do? So let's say you look at an e-commerce site, or even let's say YouTube videos, you look at plot here, what you see is the product ID on x-axis, and y-axis is here I've written it as sales, but you can think of it if it's let's say a video at let's say YouTube, it's like number of views. So you have this, and what you can do is maybe you can just focus on a small number of products that will get very high sales, but that is easy. But what also the recommendation engines allow you to do is this long tail. So there are lots of products which have very small amount of views or visibility or sales, but they do have some data. So what you can do, if you were a person actually in the store, then you have limited bandwidth. You can only focus on a few products. But these recommendation systems are automatic. So by using the algorithms, you can actually focus on this long tail and get them to realize sales for even the long tails. Okay. So there are different types of recommendation systems. So one type is substitutes, right? So let's say you bought a mouse and then it comes related products with free delivery on eligible orders, right? So you are seeing all the mouse substitutes. So one product you have shown interest in, another product are kind of substitutes. Other type is a complementary recommendation. You bought a mouse, you put the mouse in your cart, then it says, oh, by the way, keyboard is frequently bought together with the mouse, so you can maybe buy the keyboard. So you are no longer trying to sell a mouse because you've already put the mouse in the cart. Now you want to sell other products which may be related to that product. So that's a complementary recommendation system. The third one is kind of personalized. So you have a browsing history. Based on your browsing history, either a mouse or a tweezer or some products like this, it suggests. Right? So this is a personalized recommendation based on the user's history. Yeah. So what is this type of recommendation? Customer who bought this product also bought. Huh? We just talked about 3 types of recommendation. Huh? Complementary. Why?
After bought this, he also bought the relevant.
Customer who bought this item also bought. Yes. So it's a complementary. Yes, you're right. Fine. After buying a mouse, you also buy a keyboard or most likely, or the screen, or a HDMI cable. Okay. What other customers do? What other items do customers buy after viewing this item? Complimentary? What other items do customers buy after viewing this item? Substitute. He has not bought the item yet, he is just viewing the item. Right? So, yes. So, in this case, I was at the mouse page and it was showing me, mouses. Right? So, it's a substitute. So, there are very different types of recommendations. And the algorithms that you use to generate these recommendations will also be very different. Okay? Top picks for you. That's a personalized recommendation. Yes. Yeah. So I bought this Ayurveda product, it buy this, yeah, so it's kind of this. Okay. So this picture actually shows that this long tail has a lot of value. It has a lot of value proposition, and that is what actually makes the e-commerce sites much more attractive than physical store, for example. So earlier people used to go to store to buy a movie or a DVD or rent a movie or a DVD, right? And that store had an area, right? It had shelf space, a limited shelf space. So that store could keep only a small number of products. Now, today you want to watch a movie of 1960s that was somewhat popular but not very popular at that time. Now, it doesn't cost much to store them at the back end in a server somewhere and stream it to you when you need it, right? And there are many such products like that, right? Even in a e-commerce site like Amazon or Alibaba, there are so many different types of products. And these products actually have a lot of, even though the volumes of each of the product is very small, but since you have an automated algorithm to generate the recommendations for these products and to carry out the transactions, this is, it creates a lot of values here. So here this graph shows, for example, Rhapsody, I think it's a music service, right? 22% comes from the long tail. Amazon.com, 57% of their revenues, the sales, comes from these long tails. And here Netflix, 20% comes from these long tails. So we have to take care of the long tails, and putting it on the web is absolutely zero cost, essentially zero cost, very close to zero cost. And the more choices you give to the customer, the better satisfied they are, right? Because then they can get anything they want at the e-commerce site. Okay, fine. Now, what are the key problems? That how do you give a recommendation, right? So you need some label data to give the recommendation, right? How do you create the label data? How do you get the label data? So, for example, if you are looking at the movies, then customers hopefully will rate the movies, and then using those ratings you can figure out which customer will like which movie. But then getting to know the ratings is a difficult problem. Right? So there are known ratings and there could be unknown ratings also. Like, for example, a customer watched a movie. That is also saying something to you, no? And a customer maybe browsed the movie title. That is also saying something. Or maybe watched the movie trailer. So that is what is called the implicit ratings. Okay? So in some cases you have explicit rating. You buy a product at Amazon.com, you leave a feedback, you leave a star rating, or you take a Ola or Uber, you leave a rating, that's an explicit rating. But there are also implicit ratings that how much time you spent on the product, right? Whether you actually bought the product or not. So those are implicit ratings. And then how do you extrapolate from this? And what is the thing that you want to optimize? The CTR refers to what's called a click-through rate, and profit refers to the profit that you earn, and revenue refers to the revenue. So there are different metrics, and the businesses may want to optimize different metrics depending upon their business needs. Okay? Yeah, so we talked about ratings, explicit and implicit. Yeah. Yeah, so explicitly ask people. Implicit is, learn from your user behavior, and, using that you try to extrapolate. Okay. So how do you actually give a recommendation to a user? So given a user is browsing a product, you have to come up with the utility, somehow the utility of the user. That how much a user is going to value a particular product. And that utility is very, very sparse. Because users have only rated only a few products. Or users have only browsed a few products. But there are many, many more products like that. So how do we actually figure that out? So that's a major problem. And there's also a cold start problem, which is when you get a new user, then you don't have any information about the user's preference or likings. Maybe there are some users who love thriller movies. There are some users who love, comedy movies. And they've already watched and rated some movies. So then you have the training data for those users, and you can, recommend movies to those users. But if a new user joins the system, you don't have any training data for that user. If you don't have any training data, then how do you figure out what movies to show him or what movies to recommend? This is what is called a cold start problem. Right? Similarly, a new movie comes into the system. Right? News release is there. Now, for this movie, for the older movies, you have people's watch history. You have the reviews posted by people. And for new movie, you don't have that. So you again run into what is called the cold start problem. So those are the kind of problems that you have to sort of solve to build the recommendation system. So how do you get the ratings, implicit versus explicit? What is the metric you want to optimize? And how do you, so the ratings could be explicit or implicit. And then how do you solve this problem of utility? How do you figure out which user is going to watch which movie or like which movie? So those are the three main problems that one has to address while designing the recommender systems. So there are different types of recommendation systems. One is what are called content based, other is collaborative filtering based, and then we have hybrid, which is combining both those two methods, and then there is advanced, which is neural networks and deep learning based, which kind of combines all these ideas together. Okay, so this is kind of like a taxonomy of recommendation systems. Okay, let me see. Okay, yeah. So content based, collaborative, and hybrid. And in collaborative filtering, we have model based filtering, clustering based filtering, matrix factorization methods, and then deep learning based methods, and also memory based filtering. And this could be user based and item based. So this is sort of like a broad category. But let's see what a content based recommendation system is. So here, when a user comes to, let's say, a site like Netflix, you want to recommend him movies. So what do? We look at the user's preference for the types of movies they like to watch. So they can, we can categorize movies into different genres, right? Thriller, adventure, science fiction, comedy and stuff like that. And then based on that, you also look at the previous items rated by the customer and look at, so the kind of items rated higher by the customers, you are going to recommend the same types of items. So for example, here in this case, movie recommendation, right? So each movie have these actors, directors, and the genre and all. So if a user is particularly highly rating a particular genre of movie, then it's more likely to like that genre again. So you're going to recommend that, or a particular actor, or a director, and stuff like that. Right? Or if you are going to a news recommendation engine, then you are going to look at the kind of news user has watched already. If a user is browsing and is looking at some news, you know what type of news articles he has watched, and then you recommend other news items which are similar in the content, okay, to that item. So what is the similarity? How do you find whether two news items are similar or not? You can have a category based, okay, so each news item you can have different kind of labels, whether it is politics, whether it is entertainment, whether it is sports and all. But can you be more specific? Because this would be just very, very highly broad category. Huh? Near? Yeah, but what? Naive bias for what? How do you find that out? So a user has watched a particular news item. Let's say he's watched 10 news items. How do you find, so you're given a basket, given a document of n documents, right? And out of which user has already watched k documents or read k documents. Now how do you find out the documents which are closest to those n documents? To those k documents, sorry. Huh? You can do some kind of nearest neighbor. How do you identify nearest two documents? How do you find the distance between the documents? Keyword count. So you can look at keywords. How do you identify keywords? Are you going to look at all the dictionary words? Then the common stop words like a and the, they will dominate the counts, and every document will be very close to each other. So what do? This you have done in your machine learning, right? You should have done this.
We can use the idea in outcome courses, which we did.
See, I'm looking for simple methods for now. I mean, obviously. Huh? TF-IDF, right? That's a very common metric, TF-IDF. What is the term frequency and inverse document frequency? So you're given a collection of documents. For each word, you find out how many times it appears in the collection of documents, right? That's your term frequency. And then the document frequency is how many times it appears in the document. Right? So using this, so the words which are rare in the corpus, right? So for example, let's look at, give me an example of a news article, some term that is there in the news which is not very common. Can you think of any news recently? Not so common. Okay, I can just do it from my area, right? Recent fMRI studies have shown blah 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 blah, something like that, right? So functional MRI, fMRI keyword, that is not going to appear in too many documents. Now if there are two documents which have the same term fMRI, and a user has already looked at one of them, then the other one is very highly likely, right? So the terms that have very low frequency in the corpus, we have to give them higher weight when we are calculating the similarity. So the IDF is the frequency of those terms in the corpus. So you divide it by the frequency in the corpus, and you also look at that term in that document, how many times that term comes in that news article. So you divide the term frequency by inverse document frequency or inverse corpus frequency, and then use that as a metric. You create a dictionary of words, and then you give this the weights, and based on this you can recommend similar contents. Is this clear? Okay. I mean, this is the early ideas. Yeah. So what you could do is, you have this data. You can look at the ratings, whether they like, what they dislike, and then based on this build item profiles. And here you can see it's a red circle and a red triangle. He likes both of them, and then the thing that is common in that is red. So you see that red is common, and then later you can match it with the red pentagon also, right? That's the common profile. So that's the basic idea of content-based recommendation feature. Yeah, so TF-IDF is one of the methods, and there are other methods also to find the profiles. So this we already talked about. Okay. So yes, what is the benefit of this? We are self-sufficient. If a user has rated some items, or you have either implicit or explicit ratings, we don't need data for other users, right? There's no cold start problem, and able to recommend to users with unique taste, able to recommend new and unpopular items, and able to provide explanations as to why you're recommending that, right? So if you're recommending a news article, there is a term frequency, and using that, and because of these terms which have gotten high weightage, that's why you're recommending it. So it can be explained also. Okay. The difficulty is that what are the features using which you compare. TF-IDF is one algorithm, but maybe you want to create other features from the documents. And how do you find, for example, in the movie, right? How do you TF-IDF in the movie, right? You have movie title, actors, directors, and genres and all of that. Now, how do you find suitable features based on this data? So that's sort of a challenging problem. And then it's a problem for the new users, that how do you build a user profile? And it runs into this over specialization. It never recommends items outside the user's profile. If a user has only liked a certain kind of items, it sticks to there. So it's unable to look at the judgment of other users. If some other users also like the same kind of movies that this user likes, and the other users like a particular movie, then you can recommend that as well. And this is what collaborative filtering actually helps you to do. And the basic idea here is so if a user is there, it prefers an item, and there's other user who prefers this item, and this is user, this is item, and this other user also prefers an item, then this could be a plausible recommendation for this user, right? Or if there are like multiple users who prefer this item, but they also prefer this item, then this could be a plausible recommendation for this item. So you basically look at other users whose ratings are similar to the current user, and then see what all other items they are rating highly, and then based on that you give that rating of to the other users. Okay. Okay. So how do you find similar users? Let's say there's a bunch of items, there's a bunch of users, and there's users have rated these items, right? You have the ratings of them, but this is a very highly sparse ratings, because each user would have only rated a very, very small number of items. You can have like millions of movies, but each user may have rated just 10 movies, right? So you have, it's a sparse rating. So how do you find similar users? Let's say the ratings are from 1 to 5. Okay? Yeah. Huh? Correlations, okay? But see, yeah. Okay, so how do you find correlations? So we can put it in the matrix form. So this is user 1, and let's say he has rated these 4 or 5 items. And now this is user 2, he has rated some other 5 items. And some of them may be common also. So yeah, one of the measure is the cosine similarity measure, which is basically, the correlations, essentially Pearson correlation, or the cosine similarity measure. And using this you can find users with high similarity. Now what do you do? Yeah. How do you recommend? So you find this similarity between the users X and Y. And now you want to recommend for the user X some movies. How would you recommend? You can look at all the other users and look at what movies they are liking and weight it by the similarity score. So you can say that, summation, so the recommendation for user X is summation over Y, similarity between X and Y times the recommendation of Y. So if users are recommended those things, so you just kind of recommend that, right? So this is essentially what it is doing. Yeah. So Rxi is 1 over k, Ryi, and okay. Either you can just weight it by similarity score, or you can find the top k similar users or top n similar users, and then just average their recommendation, right? You can do that as well. Okay. The problem with this, what's the problem with this approach? So yes, you can do that. What's the problem with this approach? The problem is that, if the number of movies are very large, you may not find too many users which have common movies that you have watched. So the correlation or the similarity that you are computing may be over a very small piece of data. Right? So you have watched only 10 movies, some other users have watched, again, 12 movies, but out of these two, only 3 are common. Or you have rated 10 movies, another user has rated 12 movies, and only 3 ratings are common. 3 movies, both of you have rated. So finding the similarity just from the 3 movies is a bit sort of not so, it's a bit dicey.
You can categorize all movies to some limited number so that you can increase the.
Yes, we can categorize, but see, the ratings are still same. The ratings you cannot generate, right? If I have rated only 10 movies, even you categorize them, then what will you do?
If there are 100 movies and the person is in the same category.
Okay, there are 100 categories of movies.
Yeah.
And then you can look at, like, instead of look at the rating at the movie, rating of the category of the movies.
Yes.
I see.
Will reduce the space.
That will reduce the space. But then this is, this would that's the initial idea. But then how do you find those categories? How do you reduce the movies into the categories? So you can use the actors, directors, and those kinds of things. So that is true. That is something you could do. Yes. And even this may work in some situations. I'm not saying this may not work, but yeah, this is one of the approaches. Okay. Then there is item to item collaborative filtering. But I'm running out of time, so then maybe let's continue in the next time. We'll just, But next time we have class on Monday, right? So Monday we have, and then Wednesday we have the presentations. Okay, so then we'll continue on Monday. Thank you.